All right, we're back to do some graphing of rational functions. This time we are going to do an example where the degree of the numerator and denominator are the same, but they're not both linear. This time they're both quadratic. And then we're going to have something else kind of special happen here too. The first thing we're going to do with this function is factor both the numerator and denominator because remember we need the zeros from both the numerator and denominator for different things, so factoring is going to be the step in that direction. Well, I know I could pull a 2 out of that numerator, which means that we actually have the difference of squares there, x plus 3, x minus 3. In the denominator, we don't have any GCF, so we're just going to have to set up our two binomials with a 2x and x to start. Okay, and I'm looking for factors of 15 here. Thinking, 1, 15, 3, 5. Do a little guessing and checking here. What ends up being what we want are a 3 and a 5, because that gives us 5x and 6x. And if I make them both negative, they look a little bit nicer. If I make them both negative, I get negative 5x, negative 6x, and that adds up to the negative 11x that we have there. So that is what this factors to. Now, the zeros of the denominator give us, so far they've given us vertical asymptotes. So it looks like we have two vertical asymptotes here at, looks like x equals 5 halves and x equals 3. Okay, I'm not going to write down what those are yet. In fact, I wouldn't write that down yet if I were you. Just bear with me here. What I want you to notice is that if we look at the actual graph, I'm just going to show you what the graph of this looks like. It only has one vertical asymptote, and that's at the value of 2.5. Okay, it does not have a 0 at 3. And you'll also notice I shifted my graph a little bit here. My window is actually going from negative 5 here up to 15, and I'll let you know why in a second. There is only one vertical asymptote. We do not have a vertical asymptote at x equals 3 like we have written right here. Oops. Okay, this is not a vertical asymptote, but it is something special. If you notice, we have a common factor in both the numerator and denominator here. What happens when we have a common factor in the numerator and denominator is we have a hole in the graph. Now, if this were just an expression that I was asking us to simplify, last week when we were doing our simplifying, we would have just said, oh, those cancel out. Okay, that's called removing that common factor. In fact, these vertical asymptotes and holes that we have here are called discontinuities. And a hole is called a removable discontinuity because it happens by canceling out those common factors. So we're going to have a hole in the graph at 3, and we'll write more about that in a second. What I would like you to do right now, though, is just rewrite that function as those two expressions over one another. And if you want to bring that 2 back in over in the top, 2x plus 6 over 2x minus 5, that's essentially what we're graphing. Okay, this is the same as this. Those graphs look identical. Okay, in fact, I'm going to show you on Desmos how identical they are. I'm in the wrong one here. Okay. So here is the graph of the original function that we have. Okay, and here it is right here, 2x squared minus 18 over 2x squared minus 11x plus 15. I just put in the whole thing, and there it is right there. Okay, in fact, if I kind of mess around with the zoom, you'll see that the vertical asymptote pops up every once in a while. I'm not sure if it's supposed to, but that's been happening on Desmos. So you kind of see that vertical asymptote. We know that it's really not there, though. Okay, now, you can't see here, but there is actually a hole in the graph. All right? We know that it's at 3, at an x value of 3. Oops. So at our x value of 3, which is right here, if I follow up to where it looks like 3 is hitting the graph, somewhere in here, I'm going to zoom in a little bit more. In fact, there's some values popping up there. If I go up a little bit higher, I don't know why it's not letting me zoom in here. I think if I go right about there, that's not going to tell me. It ends up being at 12. And if you're wondering where that 12 comes from, it actually comes from There we go. It actually comes from that other function that we came up with. Well, of course, it was letting me do it before, and it's not going to do it now, but we actually have a hole in the graph right here at 3. There it is. If I press and hold, 3 is undefined. Okay, now actually you're able to put tables into Desmos too, just by going to the edit list thing and then clicking the convert to table. And then it'll pop this table up here. And then I added these values in here. I put 2.5 in to show, hey, it's undefined. That's where our vertical asymptote is. And I put 3 in, and it says it's undefined, but it doesn't tell you what the y value is. How do you find out that it's 12? You know, besides zooming in really close on the graph or using something like Desmos here. Well, it turns out that we can do that with what we have written so far. Because if we actually find g of 3, not in the original function, not in this guy, because if we put 3 into that guy, we'd have 0 over 0, which is no good. If we put it into this one, after we remove that x minus 3, we can find out what the y value is. So we have 6 plus 6, which is 12, over 6 minus 5, which is 1, or 12. So we have, so what I'm writing here is, it's the same as this function with a hole at 3, 12. Okay? So there's a vertical asymptote at the 5 halves, but the 3 gives us a hole because it is a common factor in both the numerator and denominator. All right, let's start writing some of this stuff like we have been for these functions so far. Okay, if we started with vertical asymptotes, this time I'm going to put slash hole on there. In fact, you know, we can do that from now on. When we talk about vertical asymptotes and holes, we're really talking about discontinuities of the function. So the vertical asymptotes or hole here, or holes here, come from the denominator set equal to 0. Oops, I'm going to get rid of that parentheses. So we just have 2x minus 5 equals 0, and x would equal 5 halves. There's a vertical asymptote at x equals 5 halves. But if we take the other one, x minus 3 equals 0, we get x equals 3, that's a hole. And I'm not going to write all that stuff back over again, but the reason why is because it is a common 0, or we could say that x minus 3 is a common factor in the numerator and denominator. When it's common to both, it's a hole. Okay? So let's start plotting what we have so far. So far we have a vertical asymptote at 2.5, which is right, oops, that's 1.5, which is right here. And we have our hole at 3, 12, which I'm going to make one of my points in my table down here. Because remember how we make these tables on each side of the asymptote? I know that one important point is 312, and that 312 is a hole. Okay, so up here, 312 would be about right there. Unfortunately, it's kind of far off our graph, but there it is right there. All right, now let's start putting some of the other characteristics that we know are on this graph. Starting with end behavior and horizontal asymptotes or possibly slant asymptotes, which we'll actually get to in the next example. Well, in this case, we know that m equals n, and if you remember, that means that we have to look at the ratio of the coefficients. But let's remind ourselves why. The end behavior asymptote is 2x squared over 2x squared. That simplifies to 1. Okay, so that tells us that the end behavior is going to equal the y value of 1 as x gets really big or really small. Therefore, we have a horizontal asymptote at y equals 1. Okay, so here we have our horizontal asymptote of y equals 1. Right, the only other things that we can put on here are the x and y intercepts. X-intercepts come from setting the numerator equal to 0. Well, we've already factored it right there, actually completely factored it right there. Where you got to be careful is this. The only factor that's going to give us an x-intercept is that x plus 3. The x minus 3 got removed. That's that hole. So the only thing we're actually interested in is the x plus 3 equals 0, okay, which gives us negative 3. Oh, by the way, you could also be using our newly written simplified function, 2x plus 6 over 2x minus 5. That's going to give you negative 3 as well. Okay, you could also use that for your y-intercept in a second here too. But we have an x-intercept of -3 right there. Okay, and we have a y-intercept, and you could use either the original function or the simplified function, which is pretty cool. They're both going to give you -6/5 when you simplify. So we have the y-intercept is finding g of 0, which is -6/5. -18/15 simplifies to -6/5. So -1 1/5, which would put us right there. Okay, I'm going to find I don't know, at least one more point here. How about the point when we put in a 1? Let's see. And in fact, we're going to type this in our graph calculator to get a few more points anyways. So why don't I put in 1 and then maybe, I don't know, how about 2 as well, just to get a little bit closer to that asymptote to see where that comes down. If I put in 1, I get -2.7, and if I put in 2, I get -10. I'm just getting that from my graphing calculator right there. Okay. In fact, let me actually pull this guy over here a little bit more for us to use. Okay, that's what I'm using to get these values. So I've got 2, -10, which is right there, and 1, -2.7, which is right there. That's pretty good. That's enough for us to graph that side of the function. Okay, now we're going to focus on the right side of the asymptote. We already have that 312, that whole. Let's get a couple more points over there. How about putting in 4 and 5 over there to see what happens? When we put in 4, we get 4.7 right there. And when we put in 5, we get 3.2. There's 4. 1, 2, 3, 4.7. And 5, 3.2. About there. And we could put in a few more, but this I think is pretty good. We've got our hole right there, and just want to point out too, your graphing calculator, if you look at it, does not show the hole there. It can't. I mean, it shows it on the table. It says there's an error. Okay, and I don't even have my vertical asymptote showing up because I'm only going by ones here, so it doesn't show the 2.5. But if you look at the actual graph in the graphing calculator, I have it right here. It does not show you. That hole is 312, but it's right here. 14, 13, there it is, right there. There's that hole at 3, 12. Your calculator can't show it to you. I don't think it does unless you zoom in a whole ton. I don't think you can't see that discontinuity. So how does this affect our domain and range? Let's write those right here. Well, our domain is going to be everything from -infinity up until that first vertical asymptote, which is 2.5. And then it's going to be from that vertical asymptote until the hole, which is 3. And then it's going to continue on from that hole until positive infinity. The range looks like we take on all values except for values at the horizontal asymptote. So everything from -infinity up until 1. And then from 1 until positive infinity. And that is what happens when you have a common factor in the numerator and denominator. It ends up creating a hole in the graph.